Okay, good morning, everybody. Welcome back. This is our second lecture, chapter 7. So we're gonna have a few more. So Thursday and the next week, Tuesday, next week, Thursday is Thanksgiving, so there will be no lecture on that day. And then there will be 2 more lectures after Thanksgiving, and you guys will be ready for the final. I know, time flies, yeah.
Hopefully.
But this chapter is, as you can see, longer and seems to be more difficult than the previous ones. However, if you kind of master the basics, and you will find it very easy. So we'll go step by step. So last week, what we did is we went through MOSFET and BJT and derived the small signal, like signals, small signals. Like you have a small signal at the input, at the base, at the gate, and what expression on output. And from those expressions, we build the equivalent circuit, the small signal equivalent circuit. And so that process itself is important because you need to understand where it comes from. Okay, why is this a small signal? Why is this a small signal model? And why is this equivalent circuit? Right? But once you get through that, and in the next couple of sections in this chapter, what you're really doing is simply applying those small signal models onto any amplifier and then solve for the circuit problem. Mostly we use nodal analysis in this book. It's interesting, right? But occasionally we do loop, but mostly nodal analysis because it was easier, just by this nature of the circuits. So we ended last lecture with an example. We had a transistor and we had an input. You guys see at the input side, as we mentioned, this is a common source amplifier because the source is grounded, and we have output at the drain, and then we have input at the gate. And the input has 2 components. This capital VGS is for the DC biasing. Remember, without this one, this MOSFET will not be in saturation. If it's not in saturation, you'll not be able to use it as an amplifier. And then this is a small signal added onto the DC voltage, DC biasing voltage. And when we solve the circuit, we started by using these 2 together, but then we separate them. So we use like a superposition. But remember, again, this DC voltage is necessary for the small signal to exist. Okay. So sometimes in the future, like when you move on to chapter 8, 9, 10, 11, oftentimes they neglected this one. So they simply drew the small signal model on this diagram without the DC biasing. So in theory, that would not work. But what the rationale was, they want to simplify analysis. They know that there's a DC, but the DC doesn't do anything with the AC except with doing the provide biasing. So we simply like neglect it, saying, okay, we know that's a DC, but it doesn't do anything to AC anyway, so we're going to neglect it. So you're going to see some of the circuits that doesn't have this one, but they always say that's a small signal equivalent circuit, even though it's not small signal, but it's not an equivalent circuit, but it's actually a small signal equivalent circuit. Okay. And then from there, we found the expression VO, and then we VO as a function of VGS, or we find the current ID as a function of VGS, we derive that GM. And then from GM, we find the output of VO as a function of VGS, and we derive the voltage gain. Remember, the voltage gain is a negative signal, is a negative value, right? So that's what we did. And then also we talk a little about finding the range, because if you look at the circuit over here, the capital VGS is for biasing. And when you add a lowercase VGS onto that signal, you can imagine that the operating point is here, but then your signal can go up and down, right? So if your input signal is too big and it's going to exceed, it's going to make this thing like out of saturation. So that's not going to work. So the maximum value of your AC signal to keep the transistor in saturation is your range, your input range. And of course, that also gives you output range. And you can, from input range to find output range, you can also, for given output range to find the input range. And they're corresponding to each other. Yes.
When you say saturation, you mean like the non-linear mode?
No, the saturation for MOSFET is a linear region. So you have to keep it in saturation. Maybe I said it wrong, but you have to keep it in saturation. Yeah. Yeah. So if it's out of saturation, you're out of luck because it's no longer linear. But for BJT, it's a different. Yeah. The BJT, we have to keep it in the linear region, not the saturation region, right? So we talked a little bit about biasing, so this will be quick. If you plot VO as a function of VGS, so this little VGS over here is the input, and the VO is over here, and we call it VDS here. If you plot the relations, you'll find that this kind of a curve like this. And so apparently, if we bias the point, the capital VGS in the middle, that's the best because you have your maximum range, maximum swing of output or input. Right? So if you like work at this point, because up is okay, but when your signal becomes negative, you go here, that's not good because you're already out of saturation. So biasing is important. So often we bias in the middle point, so between A and B. So A is the cutoff point where VGS has to be larger than VT, right? Otherwise, it's going to be cut off. But above VT, get to VB, you're out of saturation, you go to triode mode. So between A and B, we try to maintain the middle. So that's just some concepts visualizing for you guys. And if you look at basically the actual waveform at the input and output, this is what it would look like. So at the input side, you have your capital VGS is the biasing point. VT is your threshold voltage. So VGS, capital VGS plus lowercase VGS together has to be more than VT, to maintain saturation, right? So that's kind of your input signal, AC signal overlap on that capital VGS. That's your actual waveform at the input. And at the output, you get like the DC biasing output, and you have your AC added on top of your DC biasing. So this blue is your actual waveform. The dotted line, this line indicates that's the DC biasing. Without AC, that will be your output. And this is your lower range. You can only go up to here. Right? So that's really, really, really simple. Now, in real life, you might say, okay, I got a small signal input and I got like output. But the output has a DC and an AC. How do I separate these two? Right? So if you're in the lab to do experiment, you'll find it's easy when you see it on the oscilloscope, there's a button between DC and AC choice. So you put DC, you'll see the whole thing. You put AC, it will automatically take the DC out. You will see this across zero, actually. So in real life, when you build the circuit, what you do is you add a capacitor. So the capacitor, if it's big enough, you guys remember the impedance of capacitor is 1 over omega C, right? So if omega big enough, and C is big enough, 1 over omega C is close to 0. So that's basically you can get your AC. But for DC, that's open circuit, right? So that's how you get. So basically, like what you do, let's say we draw the circuit like this. So what you're doing is here, you add a capacitor, then you add your load resistance. And then here will be your VO. Your VO is going to be up there. Now for the input side, there's also different ways to get the input, but we'll touch that later on. But for now, we just add the input together, DC and AC to get the input side. Okay. So for this BJT small signal, we did derive that as well. So you guys remember the small signal equivalent circuit has a little bit difference, which means this has an R pi. The reason is you have current going to the base. So that's how we got our for our BJT small signal equivalent circuit. The only difference between this one and the MOSFET is we have RPi, and the equation expressions for how to calculate RPi and GM. You guys should write that down or memorize that. So here we can go to an example. We didn't do this example, right? Okay. So I'll probably have to get this so that we can get the actual. Okay. Okay, it's 30 some two. So what I wanted to is we together to look at the yeah. All right. So this is what was given. IS is given. I'm going to write this down so that we can work together. So IS given is 10 to the minus 15 amps. And RC is given 6.8 kilo ohms. And the circuit, if we draw the circuit, it will look like this, similar to that. So what was given was, let's write number one. So they want VCE, which in this case is actually equal to the capital VO equal to 3.2 volts. And they want to find IC. But this has nothing to do with AC yet. Basically, we're looking at the DC biasing. So what we're saying is, okay, so we have to know VCC is given at 10 volts. So those three numbers are given, RC given. So they want VCC to be 3.2 volts. So from here, we want to determine what IC is. Is that simple? How?
Formula current and solve for solve for IC.
So IC will be equal to VCC minus VCE divided by RC, right? So that will give you, which is 10 minus 3.2 divided by 6.8. So that was easy. So that's only 1 milliamps. Yeah. Let me see, what's the next question? So that one was easy to find out. Find the voltage gain at the bias point. You want to say, okay. So once we find IC, well, what we need to do is, let me see, find the voltage gain. So we need to find AV. So in order to find AV, the voltage gain, we know that, well, if you guys remember the equivalent circuit, we can draw it here. So this is what we'll be using this again. So I think we're neglecting RO. So this one will make it easier. So there should be just RC, and this VO, this V. Oh, did I use VGS? That's not right. Should be VBE. Sorry about that. This is BJT, should be VBE. Okay. So this is RPi. So in order to find AV, we know that this is, so your VO will be like GM times VBE times RC. plus give the minus sign. So that's your voltage. And of course, from here, we can find AV is equal to VO over VBE equal to minus GM times RC. So all we need to do here is really just to find VBE is to find the relation between VO and VBE. I mean, to find GM, right? So in order to find the GM, so if we remember the expression for GM, so from here, we know that this IC is 1 milliamp and VT is 25, so it's 1 over 25, 0.04. And we're plugging this back into this equation over here. So we get AV equal to 0.04 times RC 6.8. That gives you minus 272 volt per volt. That's a pretty big gain. And of course, from here, we can find VO. I think that there was given was how much was given was for amplitude of 5 millivolts. So VO is going to be AV times VBE, and VBE was given 5 millivolts, right? So and from here you get AV is 272 times 5 millivolts. That gives you what? Times 5, that's going to be 1.4 some volts. So like it's going to be like minus 1.36 volts. Okay, so that's number 3, and let's see what number 4 is asking. And what's okay. For the power increment, we the rise from the H ratio. All right. So what it wants you to further go, actually, I mean, I can go to back here, you guys can read it. If the positive increment in VBE, so what does it mean? That if VBE, say, is a certain voltage, this little VBE above VBE, say, whatever this value is going to be, that little value added onto this, that would drive the transistor to the edge of saturation. Remember, this is a BJT, so that means it's going to drive out of the linear range. And at that point, you have VC 0.3. So what would be this little number? Now, in order to find this number, we should first find this VBE, right? Otherwise, it would be difficult to do. So let's find a capital VBE. So remember, IC is IS e to the power VBE over VT, right? So that's what we have. Now, IS is given minus 10 to the minus 15. IC is 1 milli. So you have VBE will be something like VT times log IC over IS. And this number, let's see what the number, I already calculated. This 0.691, 0.691 volt. Let's move back.
So that's the DC bias?
Yeah, that's your DC biasing voltage. That's your VBE. So if you look at what it says here is that what it says that this, let's say this is your DC biasing. So your will. So your output will be something like here.
So the bottom of that is 0.3?
The bottom point is 0.3. If you go beyond 0.3, it's going to cut off. So what we need to find is what would be the value of this one that is corresponding to the positive input. Remember, this is reverse. Output is negative input, right? So what is the value of this corresponding to the positive increment of VBE? So what we're doing here is we want to say VC is 0.3. So number 5. So VCE now is 0.3 volts at the minimum. And from here, you can find IC, which is going to be VCC minus VCE divided by RC. That gives you how much, how many milliamps? 1.426 milliamps. So that's the current. Suppose that your VCE drops 0.3, that will be your age of your current. Okay. And then from here, you can find your IC equal to like IS e to the power VBE over VT, right? So from here, like you can say IC1, IC2, IS V e to the V. There was a delay. VBE2 divided by VT. So you see here, what you can do is you can take the ratio between these two, which means like at one point, you have VBE1, you have IC1, you have VBE2, you have IC2, right? So if you take the ratio of this one, this IS will cancel, and then you have IC1 over IC2, and then here is e to the power divided by e to the power. And then from there, you can find the relation between VBE1 and VBE2. So what we found is VBE2 minus VBE1 equal to VT log IC2 IC1. So from here, you know VT. If you know IC1, IC2, because IC2 is given here, like here, we have IC2. And IC1 initially we got was 1 milliamp. So it's basically 1.4 divided by 1, take a log times 25. That's the difference between these two base voltages. Yeah.
Why can't you just subtract 0.691 minus 0.3 and find the amplitude? Isn't that VBE?
No, 0.3 is the VCE. It's a saturation voltage, not VBE. You have to translate it back into VBE. VBE is the input. VBE is here. See? The VBE is here. The change over here induces a change in output. So the output minimum is 0.3 volts. That's VCE. So you cannot simply subtract VBE by 0.3. That's you cannot do that. Okay. So from here, we can find the actual current VBE and so on. Let's see what the next step says. And find the negative that drive transfer to it. Yeah, so this is the next step is basically the same thing, saying, okay, what happens if our input is negative to the point that the output will be 0.99 VCC? So you will go back simply to do the same equation. Yes. Oh, so I use that for simplicity. So IC1 is for BE1 and IC2 is for BE2, because for any given VBE, you got IC. So in order to distinguish between these two different values, you just simply name it IC1, IC2. No, that's the same current at a different input. VBE1, like VBE1, for example, now is 0.2 volts, and you got IC. Now I change VBE to VBE to 0.3 volts, you got another current. So it's the same circuit, but at different time, different regions. Well, not different regions, for different input. So your input is 1, your output is this, your input is 2, your output is this. So it just give different numbers, different. But you still have to use a symbol to represent it, right? Yeah, you could do that. There's nothing wrong with that. I mean, how would you solve for VBE? Like, for example, in this case, we said VBE is 0.691, right? But if you get a different VBE, if you have a different IC, and your VBE would change. So you can use the same symbol saying they all called VBE, but it just at a different time, I have a different value. Yeah.
So you want us to use VCE to find the current
Yeah.
And the ratio of the currents defined VBE minus VBE.
Yeah.
Okay.
You know, for this chapter, I think the most difficult part, well, a couple, but one of the most difficult part is to find the range. I think a student always confusing input range, output range. That's always kind of different, especially finding input range. Output range can be not that bad. So input range is typically more difficult. And also there's going to be also solving the actual circuit, doing mathematics is another hurdle for many students. So to find the range, I want to just recap with the MOSFET and BJT and let you guys do it again using this common source amplifier as example, how to find the range. And then here we have a circuit of so for output range, for example, for the MOSFET, the minimum range is the transistor goes to out of saturation. How do you maintain the transistor in saturation? Is you have to maintain VDS larger than VOV, right? So that's your minimum. So VDS has to be larger than VOV, and VOV is VGS minus VT. So VO mean is going to be VOV. That's your minimum voltage. That's your minimum output. And your maximum output, so apparently, as long as your VGS, as long as your VDS is larger than VOV, it's always in saturation. But at some point, what happens? That you're gonna reach the absolute maximum. So your absolute maximum often is just VDD. I mean, so ideally it's VDD minus ID max times RD. So it depends on how you find ID mean, not ID max. Because you have to have a certain current to maintain this in saturation. If your current goes zero, the whole thing is stopped, right? So you have to have a certain current. So in theory, you can get to the VDD, but in practice, there's a certain limit you cannot go above, right? So that's your output range for MOSFET. And then for BJT, the VO mean is going to be, and you guys know this has to be in linear range, which means your VCE has to be larger than 0.3 volts in order to be in the linear range. So that's your minimum. And then your VO max. So in theory, you can go to get VCC, but in practice, you can get, you have to find your actual minimum current. But that minimum current, again, absolute value is VCC. The MOSFET absolute voltage is VDD. So whatever power supply is that given. Now, of course, what you'll find is that usually the range. Let me do this. So usually, if you plot the curves like this, so let's say this is your. So, and then this is your range. So if you look at here, this is one example, which means you hit the bottom minimum, but you didn't hit the max. You cannot reach both. I mean, you can by design, but not likely every time you will hit both minimum and maximum, right? So we're talking about output here. Another example will be here you have So if your biasing is kind of too big, so what you're doing is you're hitting the maximum, but you're not hitting actually the minimum. So in both cases, your range, like your swing, your signal swing. So this I want to distinguish these two different things. So the dotted line is your absolute range, which means your minimum can go here, your maximum can go here. But in practice, because the voltage, the waveform has to be symmetrical, your actual voltage swing is this range. It's not going to hit the max, right? Let's say if this is 2 volts and this 2, your swing is 4 volt. Even this is maybe 6 volts, but it doesn't matter anymore. Here is the same thing. Here, what you're hitting maximum, but you don't hit the minimum. So your voltage swing is this much, not the range. So the range could be 5 volts, but your swing is 4 volts. You guys understand? So your output voltage swing is different from the absolute range. And of course, from here, what you're doing is you can easily find the input range. So the input range will be, because your VGS in this case is going to be minus VO over AV. So that's your range. And VB here, of course, is the same thing, is minus VO over AV. But of course, the minus sign here doesn't really do a lot because you're doing the range. So you could take the minus out and just take the absolute value. That gives you the input swing range.
Wouldn't it change our mins to maxes, maxes?
Yeah, it does. It does, right? It does. You're right. So your input upswing is negative here, right? You're right. So you can find, but often again when we say swing, between the signal swing, it doesn't change, but the actual range could be different because it does change the terminal. Okay.
So when finding the input range, we have to find the output range first?
Typically, yes. Typically, yes. So there's again, this will be really quick. Just a concept is that for any given circuit, and this is you can use like graphical analysis to find the solution. In this case, what we're doing is for a given MOSFET, so for a given MOSFET, we can write the two equations. One is VO equal to VDD minus ID times RD. And then we can also write ID equal to, so in this case, you can find like ID equal to VDD minus VO divided by RD. So that's number one equation. But another equation to write is ID equal to 1/2 K prime so you can write these two equations. The top equation is VDD minus VO over RD, and then second equation is ID over this. You see, this ID is related to VGS, which is the input, but that ID is related to VO, is your output. So one way, of course, what we have done is mathematically we plug it in, we got the solution. But in theory, you can also plot these two curves. So when you plot these two curves, like what happens? Like I plot the first one. The first one is ID is VO over is VDD minus VDD minus VO divided by RD. So if VO is 0, we got ID is equal to it will be VDD or RD. So it's just linear. And if for ID 0, we got VO equal to VDD. So that's the first equation. That's equation 1. And for equation 2, for any given VGS, we can plot it. That's equation 2, right? The cross point is your working point, is the operating point. So we plot for any given VGS, but if your VGS change, you plot another curve. So now the one that I draw here is probably the best operating point because it's actually in the middle. And I get like go up and down, my wheel can go up and down, my ID can go up and down, and I have the best or the maximum range that give my circuit. So that's great. So see here is a duplicate. We use VDS basically here is a wheel, and we plot any VGS, and then we plot the actual black hole is equation number 1. So you can have multiple operating points based on VGS, but the middle point is your best point. And here is where you enter the trial mode. So you want to avoid this range. So that's your like lower, your minimum output. And then here is your maximum output. So between these two is your output range.
Point for voltage is supposed to be our bias point, DC bias.
The DC biasing point, yeah. The Q is your DC biasing point. Okay. Just very quickly, you can use a MOSFET as a switch. Basically, if MOSFET in the triode mode, it's like a very little voltage drop, but once you cut off, there's no current can go through. So ideally, your MOSFET can be working as a switch. So it's like this. So this is your MOSFET. So if your VGS oops, what happened? Okay, so my VO is going to depend on VGS signal. So if VGS is well, it really depends on between the difference between VGS and VT. So that's your VOV. So if your VDS is less than VOV, what happens? It's in triode mode. And the voltage VDS is very small. It's like 0.2 volts. If VGS is less than VT, so the first condition is VGS is larger than VT. And the second condition is VGS is less than VT, and this is in cutoff. And in triode mode, it's like a short circuit because VDS is very small, so it's like a short circuit, and it's like an open circuit. So basically, well, the circuit already drawn. I don't have to draw it again. So in the triode mode, it's like a short circuit, but in the cutoff mode, it's like open circuit. So once you're in short circuit, because there's little voltage drop, like 0.2 volts, so there's some little resistance called RDS, lowercase RDS, that represent that little voltage drop. That 0.2 volts is only true for signal amplifiers, for small signal amplifiers. If you go to actual switch devices, that voltage is actually much more than 0.2. Sometimes it can go to 1 volt, 2 volts, 3 volts. It depends on the voltage level. If the switch has like 1,200 volts, for example, and the voltage drop can get up to more than 2 to 3 volts. And it's usually constant.
Just lowering VGS below VT and up above VT and back and forth. Just switch.
Yeah.
Okay.
just like input goes like this. So when VGS is big, this, and then here you can find your VO. So when VGS big, and then when VGS 0, your output is 0. When your input is big, and then it's like this. Oh, it's the opposite actually.
It'd be some signal or something.
Yeah, it's opposite because when your input is high, output is 0.3. It's opposite. Okay. Yeah, so we talk about biasing points and so on. So here we basically already did quite a bit, so I probably can skip a few things here. Deriving GM, small signal operations. This signal, we did this. Okay, I want to start here is because we actually, like I said, I didn't follow the actual slide order. I derived the equations, GM and AIV, and also I derived the equivalent circuit, the last lecture. So you guys can always refer back. But those blank space, if you want to print it, you can write down on them to review what you have learned. So let's talk about early resistance. Remember, for both BJT and the MOSFET, the curve that we had in ideal case was like flat. But then we said, well, in real life, that's actually not true. They actually go like this. And if we extend all these lines, and we got this point, we call it VA. And in the DC operation, when we talk about VA, we find that we can use RO is kind of a resistance, is 1 over lambda. Like for that, it's called channel effect and so on. And this can be different for MOSFETs and BJTs. I don't know if you guys remember, for MOSFET, this is, how do you calculate this? Sometimes I can also not remember exactly, but for you guys, it's just easy write down, and you should be able to. Yeah. So remember the DC circuit that we had was, let's look at MOSFET. And for the DC operation, we had a equivalent circuit. And then for the AC operation, what we're going to do is we're going to simply add. We can go through the process to derive it. The reason for that, if you guys remember, what we did was when with the DC operation, we had a resistor RO like this. We put it here, right? So that's how we got this equivalent circuit. So if we replace this middle one with a small signal equivalent circuit, which is this part, and you simply add RO, you get the actual circuit with equivalent circuit. But of course, you might say, well, what happened? I mean, in theory, can we derive that? You certainly can. Is if you look at the equations of ID, for example, equal to 1/2 K n prime WOL and VGS minus VT squared. That's the one linear. And then you have this one called 1 plus, was it 1 plus lambda or something? Actually, I better write down the. I don't remember the equations, but guys, you can look it up later. So this one actually increases the value as this channel effect goes more and more. So that's where we separate these two terms, and we got the DC equivalent circuit where we have not only just this current, but actually there's another term. So with this term, we actually converted that into another term. It's like given to ID, which is 1, and then plus there's another one, maybe ID over is V, what is,
It's one plus beta V times VDS.
oh, times VDS, right? Yeah. So it's going to be VDS over RO, right? So it's like another term added to the actual current. And we can use this same equation for the small signal, but it's just going to be a tedious process. So I'm not going to go through that. If you guys are interested, you can practice yourself. But what the end of the day, what we are doing is we are saying this not only impacts the DC biasing, but actually it also gets some impact on the small signal. And with that small signal is that you add this one onto the transistor. So that's going to be your early resistance. So in the future, actually, we do this a lot with RO because sometimes if you don't have a load, if we look at the equivalent circuit of well, maybe probably not today, but when you have, sometimes you have an amplifier that doesn't have a load. If you don't have a load, where would the current flow? No, the current has no flow because there's no pulse. So what you have is actually it can flow by itself inside the MOSFET because it got this resistance, early resistance. So actually the circuit will still work. Yeah. So get to that point, and then this is for to add. Okay, so this is kind of interesting. What I mentioned is that the circuit to the left is the small signal model without early resistance, and then the circuit to the right is the circuit with early resistance. Now, at this point, if you don't have any resistance connected at the point of D, you still get an output, which is GM VGS times RO. So that's when you guys go into chapter 8, like doing the current mirrors, often you don't have a load resistance. You use the RO as a load. So that will give you a certain output at D. Okay. So I think by this point, well, you guys need to kind of memorize this equivalent circuit. So if your problem is given, say, neglect early effect or neglect channel effect, the RO goes away. So don't worry about it. But if it does give you VA or does give you lambda or something, you need to put the VA in that circuit. So just like you might say, okay, how do I know I put RO or not RO? You just look at whether it's given. If VA is given, you need to put it. If VA is not given, which means VA is infinity, so IC over VA is kind of 0, so you don't put it, right? So the reason I say we need to memorize this circuit is because in the future, you will start to look at, for any given amplifier circuit, you would go in there, dig out that MOSFET like symbol, put this equivalent circuit there. And then you draw the components around it, and then you solve for the circuit problem. So it's as simple as that. But of course, we still have to introduce a few concepts saying what exactly like common source mean, what is it a common collector mean, things like that. So here, just one more step to put in perspective is that if you have RO, this blue part, you guys see, this is the MOSFET. So the process of doing equivalent circuit, this is a simple one. We'll have much more complex one in the future. So when you guys in the future do this, is isolate like the MOSFET. The step 1 is look at where's the MOSFET. And then the second step, so that's step 1. And the second step is draw the equivalent circuit model of that MOSFET, or BJT. So okay, draw that. That's step 2. And step 3, find what components are connected to each terminal. Yeah, go ahead.
So in that diagram going to that diagram, what happens to BDD?
What do you think?
Well, I would assume that it would be, because since we have the voltage and I don't understand why RD is in parallel with RO is my main question.
Yeah, we'll get there. We'll get there, okay?
That's fair.
We'll get there. So think about it. When you do superposition, what do you do?
Voltage source.
Right, you don't,
Well, you do one voltage source at a time.
yeah, and then what do you do for the other voltage source?
You act as if it doesn't exist.
It's shorted.
Yeah.
If it's the current source, you open it. Right. So
So we're doing just the small.
you're doing just a small signal. So for the DC voltage, it's a short circuit, which means VCC is a ground. Right? Okay. So now let's find out. So what is connected to the gate? We need to find out. And VGS and the VGS, so lowercase and capital V. But we are talking about small signal. So the capital VGS is
Just a small.
just the short circuit. So that's what we got for the gate. And then what is connected to the source? Ground. Simple. And what is connected to the drain? Resistor. And of course, you can connect resistor like this way. And where does the resistor go? Like we discussed, it goes to VDD, and VDD is a ground for AC. It's a well do you superposition, so it goes to ground, right? So you know to make our eyes, please, look it better. So instead of doing there, we connect to ground. And where's our output? Between RD and the model, right? So that's your VO. You see here, it's that simple. So you have to find out like you follow the 3 steps. First step, identify the MOSFET. Second, draw the equivalent circuit, small signal equivalent circuit. Step 3, find components that are connected to each terminal. And make sure, of course, here you short the DC voltages. If there's a DC current, open it. If there's a DC voltage, short it. And we can probably go through a couple of like maybe one more like example. I'm going to use this slide to give you guys like a very maybe let's say kind of a complex example. And we're just going to do the equivalent circuit. We're not going to solve the actual problem. So what we're going to do is I'm going to give you a circuit like this. Yeah. Well,
we're only doing the small circuit.
Well, actually, this circuit is very popular. You're going to see in your exams. But
What is that circle right there?
The small signal. Or is it the total?
Yeah. Well, no, it's just a small signal. Yeah. Oh, actually, I made it this one. I should have tried it this way. Yeah. Just make some corrections.
putting in the equivalent circuit.
Yeah, we're just trying to find the equivalent circuit, right? So,
And that four-way intersection is a dot and not just the wires passing through each other.
what is it?
I assume there's a dot at that four-way intersection.
Yeah. Yeah, of course, yeah, every cross there's a dot, yeah. Okay. So what we're doing here is we try to find the equivalent circuit so that we can later on to solve the problem. But first of all, I added a couple of capacitors. And this is what we call like a bypass capacitors. And secondly, I added current source. Do you see that? Yeah. So the current source, of course, is sort of for biasing purposes. But here, often if you have DC biasing at the gate, you don't need the current source biasing. But of course, here for increasing the complexity or understanding the basic principle, I just added both. So step one, find the MOSFET, right? So of course, you guys see the MOSFET, right? So it's easy to find it. So we're going to use this large space over here. So I'm going to draw the equivalent circuit of the MOSFET. So that's your MOSFET. I found it's in the middle, so that's the MOSFET. Now, step three, we need to find what terminal, what component is connected to each terminal. So we can start from any terminal, but we can start from the left, make it easier. Okay, look at the gate. What are connected to the terminal, to the gate?
A four-way intersection.
Yeah, we got a four-way intersection. We got a couple of things connected. Okay, so let's mark them up so that we know what it is. Okay, I'm gonna call this R sig. I'm gonna call this RG1, RG2. I'm gonna call this RD. I'm gonna call this RL. I'm gonna call this C1, C2, C3. Okay, so first of all, we have RG2 and RG1. They're both connected to the gate. And RG2 is easy. RG2 is connected to where? To ground. How about RG1?
Also, the small superposition, small signal. And
So-
just another resistor.
RG1 is connected to voltage source, and voltage source is a short circuit for AC, which is ground. So RG1 also goes to ground. And how about, well, you got the CC1 here too, so we can put the CC1 here. But we don't do this in this class, but in the next class, you actually have to include CC1 so you can find the frequency response. But here, let's say CC1 becomes a short circuit for AC, because 1 over omega C approach 0. Large. Frequency is high, capacity is high, so it's 0. Okay, so short circuit. So here is a short circuit. So for C1 is a short circuit. And then next we have R sig, right? And then we have your input VGS, which is connected to ground. So now you got your gate complete. That's it. Now we're going to look at the source. What is connected to the source? That current source here is a DC voltage. Okay, it's got ID, like some sort of DC current. So for DC current, where you're doing superposition, you just know.
Oh, treat it as an open.
Treat it as an open circuit. So that one is an open circuit, right? So actually, so this is like open. Oops.
So then we just have.
It doesn't change the color. Okay, I use blue, but it doesn't. Okay, so that is the open circuit. But of course, we also have a C3, and C3 is what?
It's just a wire.
Just wire, yeah, short circuit. So C3, C1 is short circuit, so 3 is short circuit. But of course, if you put it here, I wouldn't say it's wrong because when you look at the frequency response, it will be there anyway. So we'll say, this is almost like 1 over omega c approach 0. Let me say here, 1 over omega c approach 0 for small signal. Okay, so that's easy. Now we're going to look at the drain. What is connected to the drain?
The capacitor and we have two resistors.
Yeah.
Both going to ground. So
Yeah.
we first have is that RD?
Yeah, first we have the RD connect to ground because the VDD again is ground. And then we have the capacitor, and then we have the RL, which is also connect to ground, and then just your VO. Of course, this 1 omega C2 will approach 0 as well. So if you want to find the middle band where the capacitor is 0 impedance, you can start to solve for the circuit. So now, because now it's easy to solve the circuit, especially for MOSFET, you see what happened for MOSFET is that this is open. So basically, the left hand is a circuit and the right hand is another circuit. So it's fairly easy. The only thing I want you to pay attention is that your VO is no longer like your VO. You remember in the early stage that we said VO equal to like AV times VGS, right? But here, and that VGS for the previous example, if we go back, oops. What happened? Oh, I don't know. I can't move. For the previous example, VGS is direct connected at the gate. But here, can you see that VGS is not the same as VGS? So what I'm saying VGS here is actually wrong. I shouldn't use this VGS at all. Why I cannot erase it?
VGS is the one between the.
Yes, you're right.
On the side, right? Or on the left of it. Controls.
Okay, I cannot. So this one is wrong. Use V in, not VGS. So, I mean, we can probably go just a couple steps more to solve this problem. So what VGS then? Now, again, we assume C1 is 0. So your VGS really just the voltage divider between RG1, RG2 in parallel divided by plus R sig times V in. So that's your VGS. And then one more step, we can find a VO equal to minus GM times VGS times RD in parallel with RL in parallel with RO. Right? Those three resistors, look, this 1, 2, 3, they're in parallel. They're in parallel. So your VO will be simply this current multiplied by this. Okay. So that seems to be fairly simple. But if I want to go one step further, let's see if we have space here. Yeah, okay. If we have, let's say, here is not a CS, it's C, but a resistance, what happens? Yeah, go ahead. Not what? Oh, we just talked about it. VDD is a ground for AC. It's a voltage source. We're using superposition. So for AC signal, DC ground, DC voltage is a ground, and DC current is the open circuit. Yeah.
If CS is a resistor, this becomes a little more.
Yeah, if CS is a resistor, you see, it becomes more difficult. Not only just VO is not this time this anymore because there's some here, but also VGS, you see, because this is not ground anymore. You cannot say this is voltage divider, right? So that really makes it more difficult. But of course, we'll get to that point towards like the end of the class. It's this. There are two types of amplifiers. One is called common source with a resistance as the source. That's one. And And number one, number two is common collector, or sometimes called source follower. You can actually take your output as a source with this resistance. Basically, not here. We take the output over here, and there's a resistance here. So it becomes more difficult. So to that point, so far we get this pi model. What we call sometimes we call the pi model. It's like a pi, right? So it's, this branch is especially for BJT. It does look at pi. It's like this, or it's called hybrid pi, maybe the reverse pi. You know, but so we're going to develop another model. It's called a T model. So we'll make it just what they're doing is to make it mathematically easier. Let's see what time is actually. Okay. 10 minutes, yeah. So probably what we're gonna do one example, and then we can like conclude today. Then we'll go to the let's see. Let me see what. Oh yeah. So we're gonna do the T model next week. So let's do example here. So this example apparently is no more than not more complex than the one that we just illustrated on the previous slide, right? So what we're saying here, we want to determine the small signal gain. We have VT is given, K is given, VA is given. Coupling capacitors are large, means they are short circuits for small signal. So having this circuit, as I said, step one, find the MOSFET. And step two, draw the small signal circuit. Step three, find components connect to each terminal. So we're going to draw the small signal equivalent circuit over here. Like you guys see, this is one. And step two, I'm going to draw the equivalent circuit. Now, so this one you see, VA is given, which means you got to include that RO. So this is your equivalent circuit. Okay, we got that. So now let's look at what is connected at the gate. Well, first of all, the gate has like a three kind of cross there. Let's go beyond the cross. We have a capacitor, which is 0 for AC, and then we have voltage input. So that voltage we call VI. So we have short circuit here. And so this C1 here is infinity. So, okay. But we didn't finish yet, okay? Because there's another thing connected at the gate. We didn't get it done. So that thing called RG is 10 megohms, very big resistor. Where did it connect?
It connects
From gate to drain. So which means it's like connecting here, right? Now it's outside of the MOSFET, of course, but for simplicity, I'm not going to draw it like a big circle over there. I'm going to just move it inside. That doesn't change anything, right? So I'm going to just change it over here. It doesn't change the meaning, because instead of going like outside to here, I just moved here. That's it. Because this is a line, right? So this is RG. So next, what is connect at the output? Well, first of all, we have RD. This is RO. Also, we have RD. And then we have a capacitor, which is short circuit. And then after the circuit, we have RL. Right? So now we got the equivalent circuit. So what we need to do is we need to find the gain. The gain is VO. The AV is VO over V in. Now remember, this is VO over V in, not well, V in is equal to VGS in this case, right? Because the capacitor shorted. So basically, the voltage here, VGS is actually V in, so they're the same thing. Okay, so we need to find VO as a function of VGS. Now, this problem, the complexity comes from where? Is this? If we don't have this one, it was easy because we have VO equal to just this current times the 3 in parallel, right? But now you got this resistor here, so this current actually flows not only just here, but also here. So for simplicity, I'm going to draw a equivalent circuit. I'll just make it easier. So I'm going to draw the equivalent circuit like this. I'm going to call this RL prime.
Just the total resistance.
Yeah. And of course, from here, also called VGS, it's the same thing. So without VG, without RG, our VO is just simply RL prime times GM, or minus sign, times V. So your AV will be minus GM times RL prime. And RL prime is the parallel of RO, RD in parallel with RL. So that's without. But with RG, our VO is going to be, let's call this IL. It's going to be minus IL times RL prime. But this IL equal to GM VGS minus, so this like, right? So if you have this is called IG. Let's call this IG. So it will be minus IG, right? So what is IG then? How can you find IG?
VGS divided by RG.
No, terribly wrong.
IG.
So IG is going to be V in minus VO divided by, that's voltage difference between the two terminals. You see VO and V in. So V in minus VO divided by RG gives you that IG. So now you can plug in this back. And then from there, you plug in back here, you got VO. So the actual expression is going to be a little bit complicated. Let me see. Of course, we have to find our, like, actually, I mean, from here, I just simply give you the equations. Let's see. We have, yeah, it's quite complex, actually. So AV is equal to VO over V in, and equal to minus GM RL prime times 1 minus 1 over GM times RL, 1 plus RL prime RG. But the thing that RG is a quite big number. So this one is actually approach like a 0, very small. RL is like 10K, this is like 5 meg. So that's like 0.001. So this one is very small. And this one actually is also very small because this number can be quite big in the kilo ohms and so on. So this 1 minus the whole thing here really actually approach very small number, maybe 0.99, 0.999. And eventually your gain is approximately GM times RL prime, which is just saying that if there's no RG, this will be your output. So that's what we get, the output now on the previous slide. So with RG, your gain does reduce a little bit, but not very much. So that's what the RG does it for you. But also, to get the final numbers, you guys need to find out like what the ID is in DC. And from here, you got minus VT squared. That's how you get your ID. And then also you can find, so this is what I calculate, 1.6 milliamps. And VOV, you find it 2.9, and then you find VO and so on. Okay, and what else? So I find RL prime equal to 4.52 kilo ohms. And here you have to find this RO first. So RO is going to be VA over ID. That gives you 47 kilo ohms. And then you find GM. GM, remember, GM equal to K times VOV, which is Kn is 0.25 times VOV is 2.9. So that gives 0.725 per volt. So finally, we got VO is, I don't have the number. Okay. So I think we're going to stop here. You guys can plug in numbers to get out the actual number. As we move on, we're going to see more and more examples, and some of them are fairly easy, sometimes it's more difficult, but we always follow the procedure. Find the MOSFET, OBJT, draw the small signal equivalent circuit, find the components connected, solve the circuit. That's it. Okay, see you next time.